All right, so day 2. It still measures a variance. So obviously standard deviation is probably going to find its way in here somewhere. But now we're going to say, well, what if we don't know the data that we're given is the population? What if we only know it is a sample, which is much more common? Okay? So for sample variance, it's going to seem as though you're writing a lot of the same information you wrote the other day. It's the mean of the squares of the deviation of a sample set. Again, remember, we square it for what reason? Yeah, make it so that the total's not 0, exactly. Because if you don't square, we're going to have some negatives, especially if you calculated the mean properly. You better have some negatives in that deviation column. And so we square it to make them positive. So I'm hoping, now seeing this is sample variance, we, instead of using, remember for variance, we used sigma squared the other day, right? That was for the population. Notice for a sample, we just use S. Okay? Instead of the sigma. And then I'll let you look at that for a second and write it down. And then we'll see if you can note the difference from the population calculation and this sample calculation, other than the S thing that I just pointed out. Any differences between this one and the other one? Yes. Okay, no mu, exactly. It's x bar. Very good. Anything else? Yes. Yeah, it's a lowercase n minus 1 that you're dividing by. Before, it was a big old capital, just n, right? You just divided by what you had because you knew you had all the information. The reason you divide by n minus 1 is actually a rather involved calculation that deals with calculus and all sorts of fun things as to why they divide by n minus 1. The short answer is that it makes sure that they do not divide by too much and make the standard deviation too small. Okay? And so it's basically a way for us to try and make the sample more accurate to the population. Okay, so you don't divide by n when it's a sample, you divide by n minus 1. Okay, and really that's the only difference if you look at it. Because the mean is still in the same spot, except it's x bar now instead of mu, which somebody said, right? But otherwise, it's the same calculation. Again, we square it to make it positive. Okay. Unfortunately, having that squared means that we have different units than what we started with, correct? The mean might have been in inches, now we have square inches. Well, that's not very helpful, is it? So what do? To get it back to inches, we take square root to get the standard deviation so that it's all at least where we started, right? So it's the square root of that sample variance. And so, yes, this looks rather involved, but it is just the square root of all of that. Okay. Questions here? I know I've told you to, dig into those questions like the dividing by n minus 1, but unfortunately this one is a little bit more involved. It would take us a while for me to get you there. And not all of you have gone through calculus. Okay. Everybody ready? All right, so let's say we've got that same data from the other day, and I think I actually put it in there for you this time, right? Notice once again that no matter what we do, even though it is the sample, if it's done properly, and obviously let's say you round every once in a while, that might not be exactly 0 in that column, right? But it's going to be really close. And then so then we square it again, so we've seen that data. So in other words, really we're saying, if you didn't notice up here, that now we're saying this is the sample. Okay? It is not the population, this is just some of them. So apparently the company got larger. All right? And so do you notice though, that isn't that the exact same number we got the other day? Should it, if you think about it though, should it be the same if I'm looking at the same data? It should. Now here's where the change is going to come. What's going to be a little bit different from then what we tried to finish off the other day? I don't know if I have it down here or not, do I? Is that on the next page? I don't know, where is it? It might be there. It could be hiding on me, I don't know. Oh, there we go. So we're going to divide by n minus 1. So we're going to divide by 9 today because there were 10 bits of data instead of dividing by the 10 that we divided by the other day. So is this 9.83? Yeah, I think yours is just going to be underneath. Just write it underneath for you, I think. You have room underneath. I didn't. Is that number the same as the other day? No, it's very different. Is that number larger than the other day or smaller? It's larger because we divided by less, right? We divided by 9 instead of 10, so it makes sense, okay? Because it was 8.85 the other day, right? So with that in mind, is our standard deviation going to be larger? Now this is, we're saying we believe the population standard deviation to be this, or you could just say that it's the sample if you want, sample standard deviation. Will that be larger or smaller than what we had the other day? It's going to be larger. And the reason they want to do that is they want to make sure, well, what if there is some extra data that wasn't in here? Because remember, this is a sample now. What if there was data that would throw this off a little bit? So it's almost like they're hedging their bet a little bit when they do this calculation. And really all you have to do is take the square root of that up there, but I've made this rather involved. There you go, just to show you that it all comes out the same. Yeah, just a coincidence that it seems to begin like pi. So on average, they're saying the data deviates from the mean by 3.14. But that's kind of taken into consideration both directions, to the left and to the right of the mean. Everybody got that? Good? Yeah? No? Okay. So here's interpreting standard deviation. So let's look at it graphically. So we'll do a couple together, and then I believe I have some for you to attempt on your own. So we'll talk about these first. Do you agree that x bar in this very first one on the left here, the mean is 5 if you look at that data? Well, if everything's at 5, I could add them all up and divide by how many there are, but I'm going to get 5. Now, is there any other data here? So does the other data vary at all or deviate from the mean at all? No, so the standard deviation, if I actually did the calculation, would be 0. The reason is when you did this column right here, what would every single one of them be? 0. So yeah, you could square it, but when you square 0, you get 0. And then, yeah, you could divide by a bunch of stuff, but that's still 0. You could take square root, that's still 0. So you see the calculation does actually hold true. Okay. Now this next one, I think we can agree that the mean, this is very symmetric, correct? So you could kind of look at this, when you add things up, this data weighs the same as that and kind of calculates in. That one weighs the same as that. So do you see how the mean would actually end up at 5? The average of your data? Again, we could sit there and actually do that. We could say I've got 1 3 and 2 4s and 4 5s. You could actually do that and calculate it out, but I'm hoping you can look at these graphs and get a pretty good idea what the mean is. And so standard deviation of approximately 1.2. Okay, so they're saying the mean's here, standard deviation of 1.2 that way and 1.2 that way. Do you think on average that's about how much the data varies? Is some of it on that side and some of it on that side? Some on that side of it and some on that side of it? Yeah. And do you think they kind of would cancel out with how much they deviate from the mean? Yeah. Okay. And I'm going to give you a nice helpful hint in a little bit as to how you can locate that one standard deviation. How about this last one? Do you agree that the mean is 5 still? Even though 5 isn't one of the data values. Because really, how many 2's do I have? I have 3 2's, right? 1 3, a 7, and then 3 8's. If you actually added those up and divided by how many you had, would you get 5? Yeah, you would. Now, on average, how much does it vary? So here's your mean. So it says 1 2 3, 1 2 3. So do I have some data this way and some data that way? Some here and some there. And it's about, at this point, about a 50-50 shot on that, correct? About half on one side, half on the other? Okay. That's what we're looking for, because we want, on average, it to deviate, in this case, 3. Okay? Now, there may not be questions yet, but I want you to try these. Estimate the standard deviation. Now, we know this is the population standard deviation because, well, they're saying they used n as 8, and they have mu as 4, right? So the first one should be pretty straightforward, number 1. Number 2, maybe not as easy. Number 3, I don't know. We'll see what you say. So take a second to actually try and find what you believe the standard deviation to be. And so if this is the population, what symbol should you use for your approximation? Not S, but the O with a line. Okay, sigma. Okay. Yeah, use the S when it's the sample. All right, seems like everybody had time. Again, if you're actually listening to the recording, actually pause it and try them. All right, so this first one, the mean apparently is what? 4, right? Not apparently, it just is, right? And what would you say the standard deviation is then? Yeah, I don't even have to put an approximately on that one. It just is 0. Okay, what would you say the mean is for this one? Well, 4, because it says so right there, right? What do you think for a standard deviation this time? Yeah, it's about 1, right? I mean, let's face it, I go there and I go there, about half's in there, half's over there. That's good, yep. And how about this last one? Probably a little bit trickier. So you're saying 1, 2, 1, 2. Yeah, somewhere around 2. Seems like a pretty good one. It's probably a little bit more than 2 when you actually do the calculation, but it's pretty close. Yeah. I like those. Questions so far on standard deviation? Yes? You can think of it that way for now. I'm going to give you a much better percentage to use. What the person said is once you kind of find the mean, kind of look to the left and right, almost like a quartile thinking idea, is cut what you have on the left side in half and on the right side is half. And that's pretty close. That's going to get you close to an estimate, yeah. But I'll give you better percents here in a little bit. When we talk about something that I know another teacher in this school talks about quite a bit, the bell-shaped curve, but we're going to put actually data to it. Okay. Where is the mean on this picture? In the middle. Okay. X bar is going to be in the middle because if you did have a data that somewhat followed this shape, isn't that where it would be if it is symmetric like this? The lefts and kind of would work their way in and they would average to that. Notice here this says X bar plus S and X bar minus S, but just one of them. So that means one standard deviation to the left and one standard deviation to the right. If you do that, if you actually go that far out, and it is this bell-shaped curve, within these two, you should have 68% of the data should fall in there. If it is, the question was, is that always true? And if it is distributed at least closely to this bell-shaped curve, that's how much data will fit in there. Yes. And we are going to reference this quite a bit. This is sometimes looked at as a normal distribution, or the standard normal distribution. Okay. So now notice, what if I went out a little bit further? Let's say I went 2 standard deviations. So now it's 2 standard, that's why it's minus 2s, minus 2 standard deviations, and plus 2s, so plus 2 standard deviations. So if I went that far. And now, how much of my overall data should fit within 2 standard deviations? Now remember, you're going out twice the average now of how much the data deviates from the mean. So should you almost have all of it at that point? If you're going out double the mean, you should almost have all of it. But the ones that we're not going to get are the ones that are way out there, right? The data that's way out there, we're probably not going to catch by going that far, right? So how much are we covering there? Well, we already had 68% in the red. We're adding how much here? Basically 27? 95% you're thinking? Yeah, oh, look at that, 95%. Boom, within 2 standard deviations. Okay. Now, once you go 3 standard deviations, that's 3 times the mean. Does it make sense that we should almost have everything? Yes. Is there still a chance that there might be that one data way out there? Either way, right? It could be above the mean or below the mean. Okay. The hardest part for a lot of people to understand is where the mean is in this picture. And if you have that figured out, I think you're okay. Okay. And the mean should be somewhat central, correct? That's why it's a measure of central tendency. Okay. Should be right about in that middle. Now, How many data do you think is actually going to distribute perfectly like this? Very little. But is there going to be a lot of them that are close? Yes. So that leads us to why we can't just give you that set answer in statistics, because none of them match up to this perfect. Do they get close? Yes. Okay. But not all. Now, I know not all of you have gone through calculus, but I can give you a very helpful hint on how to find where that one standard deviation is. I know for at least one of you in here, this is going to make huge sense right now, and for some of you it will later. Okay? There is something called concavity. Okay? This is what's called concave up. Normally when I say concave up, it looks like a smiley face. Do you agree that that looks somewhat like part of a smiley face that I've done in blue? Okay? Concave down I normally refer to as a frowny face. Would you agree that right about here is where it switches over from a frowny face to a smiley face? Okay? That's where one standard deviation will be every time if it's a standard normal distribution, where it switches from frowny face to smiley face. Okay? Or where it changes from concave down to concave up, okay, which is called a point of inflection. Okay? So that is where you will always be able to find that. So now if we go back perhaps to, say, one of the harder graphs here, do you see how that actually kind of would happen in this one? Because this one's pretty symmetric, right? Where it switches from, right? Right? So this particular one is about, I think this one's about 1.2. Can you maybe see the 1.2 a little bit better now? For standard deviation, that's about where it changes over from frowny face to smiley face, right? Okay, is that helpful? Finding one standard deviation? Okay. All right, here we go. In a survey conducted by National Center for Health, the sample okay, height of American women is 64 inches. I think that's right. That's, what do you think? Is that right? 64 inches is the average height of American women ages 20 to 29. You think they're a little taller? Now it gives you a standard deviation of 2.73 inches. So again, think of it this way. If I go 2.75 inches above that and 2.75 inches below that, what percent of women should I be catching when that? 68%. Now what do you think? Is that possible? Or do you think the mean's still a little low? Okay. Now if I go out another 2.75 inches either way, I'm going to catch 95% of women. So we're going up to, let's just call it 3 to make this easier to talk about. We're talking to going up to 70 inches, almost, right? Because I think you guys think it's low, right? So let's talk about the high end. You think we're catching 95% of the women at that point. Okay, so is this maybe better than you thought initially? Okay, I know that that number is a little shocking at first, okay, but it might not be that bad. So let's estimate the percentages for the following criteria. What if their height had to be between 64 and 69.5? Well, let's find out what that difference is. What is that difference? What is it? 5.5 is the difference, right? If you did 69.5 and subtracted the 64? Well, let's find out how many standard deviations that is. Well, how do you know that? Yeah, if I divide by what one standard deviation is, would that tell me how many standard deviations that is? You're actually doing something right here that is a very huge calculation that we're going to be doing. You find out how far it is, divide by what one standard deviation is, that's going to tell you how many standard deviations away it is. It's not always going to come out to a whole number. Okay? We have really big tables that will help us solve that. The question was, what if it doesn't come out to a whole number? And we have big tables that are going to help us solve those. Okay? It's going to get us down to percentages within the hundredths, the tables. Okay? So this ends up being 2 standard deviations, and it is above, do you agree, right? It's bigger. Okay, so how many would be between 64? Well, here is our mean, right? We went 2 standard deviations above. Are you with me on that? We didn't go below in this case, right? We were strictly talking about above, right? So we know from here to 1 standard deviation is 34%, right? And another 13.5% on that next one. So what percent are we looking at? 47.5, I heard. Do you agree with that? Do you agree with that? Do you think that's accurate? That between 64 inches and almost 70 inches, we would catch almost half the women? That's very possible, right? How about a height between 58.5 and 67.5? Now here's where it gets a little trickier. What you might want to do is you still want to reference the mean in each of these. But do you agree that one of them is below the mean and one is above, correct? Okay, so let's just find out how is that in reference to the mean. So let's take 58.5 minus, because you do notice in the calculation, you always take the data minus the mean, correct? So the mean is what? 64? The reason we do this is if you do it that way, because here's your x minus x, that's what the formula tells you to do. Do you agree that if 58.5 is below the mean, correct? So shouldn't it be a negative standard deviation? It should be subtracting it. So that's why we do the calculation this way, because look at this is going to end up negative. Amazing. All right. And what do we get there? You sure? Negative 5.5? It's negative 5.5. All I had to say was, oh, are you sure? And then all of a sudden we started saying, I don't know. No, what are we going to do? Divide by what one standard deviation is, right? To find out how many standard deviations over that is. And what is one standard deviation? 2.75. So this is how many standard deviations away? 2 to the left, right? All right, so let's get a graph going for this thing. So on here, we know here, whoa. We know the mean's here, which is what, 64? And we know we went 2 this way, for sure, right? Because that's where 58.5 resides, right? In this case. With me on that? Where does 66.75 reside then? How far over is that, is our question. Well, let's find out. So let's take 6.75. You notice I'm taking the data first, right? Minus the mean is 2.75 away to the right. So divide by one standard deviation, which is 2.75, and so we are one standard deviation to the right. You with me on that? Well, we already know that these two put together is 68, right? Now, do I add this 13.5 over here? No, but do I really add 13.5 in this case? Yeah. I add the 13.5 that would be over there, right? Now, is everybody okay why we're adding those? Because some people think, oh, if it's to the left, aren't we supposed to subtract? Well, no, that's just talking about the standard, how it deviated. It was below, right? So that's why we went that way. So what do we got? We got 68 and we got 13.5, so we're looking at 81.5. So why don't you try that last one on your own right now? Take a second. So between 55.75 and 64. Whoops, that didn't work. And this is a very important knowledge to have, is the standard deviation and what it's leading us to. It's leading us to a percentage. Well, I've got how many standard deviations 64 is from the mean. I'll take care of that one. It's 0 standard deviations from the means. All right. So this one is 0 standard deviations from the mean, because if we actually do the calculation, it's 0. So we know this is our upper bound, right? So how far away is 55.75? So if I'm going to do the calculation, should I put 55.75 minus 64, or 64 minus 55.75? Which one should I put first? Yeah, because then, do you see why you're doing that, though? Because now when I actually subtract, it is going to end up being that negative that it should be, because it's below the mean, right? And how far below? 8.25, I heard. Is that correct? Negative 8.25. There you go. So we know it's definitely below by a lot, right? But now, would this answer change if the standard deviation changed in this problem? Yeah. So that's why we divide by what the standard deviation is in this problem to find out how many standard deviations it is. And I'm guessing it's a pretty nice number, right? Be careful. Not 3. Negative 3, right? So I went 1, 2. So I'm way out here. Almost caught everything between here and the... So what do we got here? We got 34, right? And 13.5. Did anybody look back to find out what the other one was? What is it? 2.35 for this little guy? Now, most people say that this should just be 50%, right? Wouldn't you think? Does it work out that way? Is it close? Yeah, it's pretty close. What'd you come up with? 49.85 is an answer I heard. Is that correct? Yep. Now, do you know what the 48.85% stands for? Okay, a half of 97. Or in other words, we're kind of looking at this saying, well, if this data up here is accurate, okay, and I just started picking random females, about how many of them would I expect to fit within those two realms? About 49.85% of them. What if I took a sample and that didn't happen? Either I took a bad sample or that data is not accurate. And that's what we're going to lead towards this year. Okay? We're going to be given data, we're going to be given samples. Is it accurate or is something wrong? Okay, is something seeming weird? Okay, any questions? And I know I'm getting some looks, and it would be half of 99.7%. Yeah. Yes.